Okay, let's go a little further into functions and talk about composition. Now, this is really going to be very key for subsequent chapters. When we talk about permutations and in fact about group elements, we can understand these in terms of composition. Very fundamental concept. Composition basically is applying one function to another function. All right, so for example, I'll give some examples here. Grandfather is father of the mother, okay? Mother of somebody. So you can say the grandfather of John is the father of the mother of John. So you take the mother of John and you take his father, and then he's the grandfather. Now, of course, you can have a maternal grandfather or a paternal grandfather. Paternal grandfather would be father of John. Okay, so you have this idea in daily life, etc. Okay, so just like a granddaughter, so if your daughter's name is Josephine and her daughter's name is Esther, then granddaughter would be the daughter of Josephine, who is Esther. So it's composition. So you take one operation after the other. Now notice you work from right to left. Okay. So you can do some of these examples. The husband of your sister, what do you call that? Etc., etc. Child of child, grandchild. You can go through like that. Okay. Well, let's do a more mathematical definition. If we want to define a function, it's good to define that function element by element. So suppose we have two functions, f from a to b and g from b to c. And we often represent these graphically. Usually when you're dealing with functions and you want to have a clear idea of what's going on, it's good to draw these sets that indicate what's going on. So f goes from a to b, and g goes from b to c. And we want to define g composed f, notice g composed f, of any particular element of big A. So let's call that element little a. So how would you define g composed f of little a? Well, if I apply f to little a, I'll get f of little a in here, and then g of this element is going to be g of f of little a. Or that's the same thing as g composed f of a. Okay, so you can do some examples of composition. For instance, here's one particular example. You take 3x and x squared. So first you take 3x and then you square that, you're going to get 9x squared. Now if you did the composition in the other order, you get a different answer. So the order definitely matters when you're doing composition. Okay, composition is not commutative. Okay. Okay. All right, so here's the warning again that you start from the right to find g composed f of a. First you take f of a and then you find g. Okay. Now there are some properties of function composition. In fact, function composition is associative. And you can prove that in this fill in the blanks exercise. Okay. Sorry, let me adjust this. Okay. And let's pass by that example. Well, let's see what we have here. Okay, so, well, here's an arrow diagram that shows in more detail the same thing that I did before. If I want to find f composed g, for instance, f of a is m, g of m is u, so g composed f of a is equal to u, and so on. Now, there's some conditions that need to be satisfied in order for the composition to be defined. The domain of g must be equal to the codomain of f. Okay. Now, actually, g composed f can be defined as long as the domain of g contains the codomain of f. And codomain is not unique. So, for instance, if I have a here, and I have b here, which is the codomain of f of a. So let's say this is the codomain of f here. I'll call that A, I'll call that B. And then I have G going between A and B. I'm sorry, F. I use F instead. I'm going to have F going between A and B. And I have another set C. Now, if I have G, as long as the domain of G contains this codomain, then I can define G composed F, because any element A in here goes to B in here, and because the domain of G contains the codomain of F, I can also define G of this element. Okay, so that's the point here. Okay, some exercises about relationship between domain and codomain of function compositions, some computations, some practical computations of function compositions, more practical computations of function composition. Now we get to proofs. Okay, and of course this is stumbling block for many people. And just like with set proofs, in some ways similar, because we're doing element by element proofs. Okay, so we want to show, for instance, we want to show that if G composed F of A is equal to A for every A, then F is 1 to 1. Okay, so we're going to prove something about one-to-oneness of this of F, given that this composition applied to A gives me A. Okay, so let's draw a picture to get this straight. And remember, F is A to B. And G is B to C. Now actually it looks like C must contain A, so A must be contained in C. It's not mentioned in the problem, but you can see that G composed F of A is A for every A in A. That means that A must be in C for any possible A. So here we have G, we have F here, and we have G here. And we start out with A here. We don't know what happens here, but we know that we end up with A over here. Okay. So we know that A is going to something, which I could call F of A. And then A here is equal to G of F of A. And I want to show that F is 1 to 1. Now, what does it mean that F is 1 to 1? We saw this back in the one-to-one chapter. You can refresh yourself. Now, I'll remind you that there's actually two ways of expressing 1 to 1. There's two equivalent ways of doing this. One is the contrapositive of the other. If you have F of A1 equals F of A2, that implies A1 equals A2. That's one way of showing 1 to 1. Another way of showing is that A1 is unequal to A2 implies F of A1 is unequal to F of A2. So these are two equivalent ways. If I can show either one of these, that shows that F is 1 to 1. Okay, so let's see which way they do it in the proof. So we want to show that F is 1 to 1. That is, if F of A1 equals F of A2, then A1 equals A2. All right, so we're going to use this form here of 1 to 1. We're given that G composed F of A is equal to A, so that's expressed by this picture here. All right, so we can refer to the picture when we're trying to prove it. Therefore, for our proof, we should assume that F of A1 is equal to F of A2, and use the given statement somehow to get A1 is equal to A2. Okay? Because that will show the implication of this 1 to 1. Okay? So let's go for it. First of all, let's try to understand why this should be true. So let me try to follow through this logic again. I'm going to get a bigger blank space to do it in. All right, so I've restated the example of what I want to prove. You want to show that if this is true, then F is 1 to 1. So let's redraw let's redraw the situation. Here I have my A, here I have my B, and here I have my C. Okay, and I know that if I have an A here, This is going to go to f of a here. And then this is going to go back to g composed f of a, which is a back again. Right. So we're going to assume f of a1 is equal to f of a2. Okay? And we also know this. Okay? We know g composed f of a is equal to a. Okay? So f of a1 is equal to f of a2. So that means I have a1 here, a2 here. And they're both going to the same place. Okay? Now, I want to use this fact that g composed f of a is equal to a. Now, both a1 and a2 both go to the same f. What about g composed f of a1? Well, by this hypothesis, g composed f of a1 is a1. What about g composed f of a2? Well, by the same hypothesis, that's equal to a2. But notice that f of a1 is equal to f of a2. Okay? So we have this. So in fact, g composed f of a1 is equal to g composed f of a2 by substitution. So these are equal by substitution. Okay? So you can see the logic here. We passed through here. We saw they both go to the same point. And of course, this point in B, when you take g of it, it goes to a unique point of here. Now, I know when I take this series of arrows here, it gives me to a2. When I take this series of arrows here, it gets me to a1. Since they're both going to the same point, it must be true that a1 is equal to a2. All right, so this is kind of a pictorial idea of why this works. So let's go back to the actual proof and see what's going on. All right, so here's the write-up of the proof. And you'll see that the write-up follows the diagram. So given that g composed f of a is equal to a, that was given as the suppose, right? Whenever you have a suppose, that's something that can be given. So for every a and a, by the definition of composition, it means that for any a1 and a2, in a we have this and this. That's the definition of composition. Now, suppose f of a1 is equal to f of a2. And by definition of a function, g of f of a1 equals g of f of a2. But g of f of a1 is a1, g of f of a2 is equal to a2, and we have the proof. Okay. All right, let's consider another example. Suppose f goes from a to b and g goes from b to c. Show that if f and g are onto, then g composed f is onto. Now, why should this be true? Let's go back to our whiteboard and see. Okay, can I scroll down here? Okay, let me just erase all this stuff. And let me copy what I want to prove, which is right here. Oh, I'm sorry, I'm doing this one. Okay, let's try again. Sorry for the delay. Just do this one here and go back to the whiteboard and paste it here. Okay, so this is what I want to prove. All right, so let's go and draw a picture and see where we are. Okay, all right, now here's my A, B, C again. All right, now here we have that f and g are both onto. So that means for any element here, for any old element here, no matter where it is, there's always something that maps to it. Okay, there's always something that maps to it. Now, also we know that, so this is f is onto. Now for g is onto, for any element in here, we know there's always something that maps to it. Now, remember when we take g composed f, then first we go here, and then we go here. Now, to show that G composed F is onto, let's go backwards. We want to show that any element of here comes originally from something over here. And it's basically a two-hop process. Any element over here does pull back to something in here, and that's because G is onto. And any element here does pull back to something in A because F is onto. So we're going to use these two facts separately. First, we're going to use G is onto to pull back any element of C into B. And then we're going to use the fact that F is onto to pull back any element of B back to A. All right, so let's see how that proof works, and you'll see it works very much the same way. Let C be an arbitrary element of big C. Since G is onto, there exists a B in big B such that G of B is equal to C. That's just what I did in my diagram. I'm pulling back an element of C into B. Now, since F is onto, there exists a A in big A such that F of A is equal to B. Now, that means that G composed F of little a is equal to G of F of A, which is equal to G of B is equal to C. Okay, so I have found an A in big A such that G composed F of little a gives me the C. And since C was arbitrary, that means that G composed F is onto. So element by element proof. Okay. Well, let's consider this next example. Suppose F goes from A to B and G goes from B to C. Show that if G composed F is 1 to 1 and the range of F is B, then G is 1 to 1. All right, let's copy this and see if we can make some sense of this from a diagram. So let's draw our picture to illustrate this. All right, again, we draw our usual three circles, A, B, and C. Okay. And what are we given? We're given that G composed F is 1 to 1, and the range of F is B. Okay. Okay, now remember, there's two ways to prove 1 to 1. One way is to show that if you have a point here and you have two elements mapping to that point, then those two elements must be the same. The other way to show it is that that G is 1 to 1 means this. It means if let's see, G goes from B to C. So if B1 is unequal to B2, that implies that G of B1 is unequal to G of B2. Okay? So let's try to prove this. This is what will prove this. And we'll prove this given the hypothesis. The hypothesis is that G composed F is 1 to 1 and the range of F is B. Okay? All right. So how are we going to prove this? Let's suppose that we're going to start with B1 is unequal to B2. And this is where we want to get G of B1 is unequal to G of B2. All right, and we have to use these facts. We have to use the fact that the range of F is B and that G composed F is 1 to 1. All right, now the range of F is B means that there must be some A1 here that maps to B1, and there must be some A2 here that maps to B2. Okay, so I can say there exists, and this is a shorthand way of saying exists, A1 and A2 such that F of A1 is equal to B1 and F of A2 is equal to B2. All right, so here I have A1 and A2. A1 and A2 are different, and I know that G composed F is 1 to 1. What does that mean? If A1 and A2 are different and G composed F is 1 to 1, that means that G composed F of A1 is different from G composed F of A2. Okay, so I can say since G composed F is 1 to 1, that means that G composed F of A1 is unequal to G composed F of A2. All right. Now, I did skip over something here. It's not possible that A1 is equal to A2 because you can't have one element mapping to two different elements in B. So here we do know that G composed F of A1 is unequal to G composed F of A2. Okay. All right. Now, what is G composed F of A1? That's just G of B1. What's G composed F of A2? That's just G of B2. So we have that G of B1 is unequal to G of B2. We've shown what we want to show. Okay? So that's the idea behind the proof. What are we using here? We started out with B1 unequal to B2. We used the fact that F is onto, that the range of F is B, F is onto, so to find A1 and A2 that map to these two different elements. Then we used one-to-oneness to get our way all the way over here to two different elements here. And then you could say we pulled back to show that G of B1 is unequal to G of B2. All right, so that's the idea. Let's go to the write-up and see how it's written up. Okay. All right, so you can see how this follows the idea that I've described. Suppose B1 and B2 are distinct elements of B. Since the range of F is B, it follows there exists a A1 which cannot be equal to A2, such that F of A1 is equal to B1 and F of A2 is equal to B2. Right. Since G composed F is one-to-one, it follows that G composed F of A1 is not equal to G composed F of A2. But by the definition of composition, G composed F of A1 is G of F of A1, but F of A1 is equal to B1. Similarly, G composed F of A2 is equal to G of B2. Okay, by substitution, it follows G of B1 is not equal to G of B2. So distinct elements of B always map to distinct elements of C, which is the same as saying that G is one-to-one. Okay, so the proof really does follow the idea. Okay. Now here's another way of doing it. We could use the other definition of one-to-one as well. Let C be in the, well, let's see if we can draw the picture first and then we'll follow the argument. So let me go back. All right, we're going to use the other definition of one-to-one. You're going to say, suppose that, here, let me paste the problem first. And let me draw the diagrams. A, B, C. Okay. Right. So we want to show that G is one-to-one. So we want to show if G of B1 is equal to G of B2 is equal to, well, let's say that's equal to C, then B1 is equal to B2. That's what we want to show. Okay? So let's see how this works out. If we have C here, and we have G of B1 and G of B2, so we have B1 and B2 here. Okay? Now, since the range of F is B, that means that any element in big B has a that maps to it. So I can find some A1 that maps here, that maps to B1, and I can find a A2 that maps to B2. Okay? But then what do I have? I have G composed F of A1 is equal to C, and G composed F of A2 is equal to C. Now, since, by hypothesis, G composed F is one-to-one, that means that A1 must be equal to A2. If A1 is equal to A2, then F of A1 is equal to F of A2, which means that B1 is equal to B2. So if I just sketch out the argument, so this is what you want to show, and here's the proof. So we say suppose, just in shorthand, suppose that G of B1 is equal to G of B2, is equal to C. And you say, since f is onto, well, I say that the range of f is B. That's the same thing as saying that f is onto. There exists an A1 and an A2 such that f of A1 is equal to B1 and f of A2 is equal to B2. Now, okay, let me erase this here. Let's continue. So by the definition of composition, G composed F of A1 is equal to G of B1, which is equal to C. And G composed F of A2 is equal to G of B2 is equal to C. Okay. Now, since G composed F is 1-to-1 by hypothesis, that means that A1 is equal to A2. But B1 is equal to f of A1. But A1 is equal to A2, which is equal to f of A2, which is equal to B2. So that gives me that B1 is equal to B2, which is what I wanted to show. I wanted to show that if I assume these two functional values are equal, then the B's themselves are equal. So that's the argument. Let's go to the formal write-up and see how that works out. Okay. All right, so let's see in big C be such that C is equal to G of B1 and C is equal to G of B2. Then since the range of f is B, there exist A1 and A2 such that f of A1 is equal to B1 and f of A2 is equal to B2. Okay, so that's just what I showed in the picture. It follows by substitution that G of f of A1 is equal to G of f of A2. But this is the same as saying that G composed f of A1 equals G composed f of A2. Since G composed f is 1-to-1, it follows that A1 is equal to A2. Applying f to both sides gives f of A1 equals f of A2 or B1 equals B2. And we've shown that for any C in big C, there's at most one little b in B such that G of B is equal to C. That means G is 1-to-1. So whenever you have a 1-to-1 proof, you can usually prove it two ways. Now I know that these exercises will be challenging, but it's very good practice, and I hope that you really get a thorough understanding of how to prove things with functions. Similarly with this exercise. So several exercises here. Okay, so I'm going to stop here.